Recording.
Okay. All right. Sorry about that, Connor, who is on the remote. Just started sharing my screen here, and so let me go back to this document for a little bit. Okay. So this document, basically, I have this table of contents here, right? And the table of contents basically list all the, 4 contests that the junior league will have, and the contents of each of those contests. So we've talked about computer number system, recursive function, and what does this program do? Prefix, infix, postfix. And today we're going to talk about bit string flicking and Boolean algebra. Those are on there. And then also let's see. And then also the digital electronics. All these 3, okay, today. And after that, we still have graph theory to go through, and data structures, and then also programming problems. Okay, we're going to talk about that in later sessions. So now let's get started. So these are what we're going to talk about today: bit string flicking, Boolean algebra, and digital electronics. Like I said, these 3 concepts sound very different, right? But on the inside, they are actually very much the same. So ACSL bitwise operation is a little bit specific, peculiar. The reason that I say that is that they are slightly different than, these languages, these real languages, because in these languages they each have a little different specifics, I would say, okay, details in themselves. Like in C, C++, you deal with integers. When we talk about bitwise operations, right, we're dealing with integers, and those integers, they're either 16-bit, or actually in C, C++, you can have 8-bit, 16-bit, 32-bit, 64-bit integers. Okay, you declare your data specifically with those sizes in mind. Okay, when you write your code. And in Java, I don't remember actually. It's probably usually the integers are 64-bit or 32-bit. I think they're usually 64-bit. In Python is very specific in that also Python actually has a concept of large integers. Okay, so the integers can really grow very, very, very large. I haven't really tried, to exhaust how big the integer can get, but it seems that even if you go to 64-bit, you can still like times 2, right? You can still make that twice as big. And then in JavaScript, it's also, I think, 32-bit and 64-bit integers. But in ACSL bitwise operation, it's really, however many bits that they give you in the problem that you're supposed to resolve. Okay, so let's say like this example here, right? It's 5 bits. Then you're just dealing with those 5 bits. Okay, by that I mean because they have these circular shift operators. When you do that, right? When you work on this integer 11101, for example, and you do a left 3-bit shift circularly left shift by 3 bits, then you're going to move these 3 bits to the backside of this string. Okay, so you're only dealing with those 5 bits, right? And so this is just ACSL, right? Not no other real languages do that, because you're always going to deal with like a certain size integer, right? Let's say if in C you're dealing with 32-bit integer, and if you're doing a circular, there's no actual circular operator in C. But if you do, let's say, or if you write a function to do that, then you're going to deal with 32 bits. Okay, this integer will be extended to 32 bits, and then you have zeros filling up to 32-bit instead of dealing with 5 bits. Okay, so this is something specific in the ACSL problems that they give you in the contest. Okay, so these are the operators that ACSL defined for bitwise operations. Okay, that's what they call bit string flicking. I don't know why they call it that, but well, so there's not operator. Not operator is basically flicking the bits, really, right? 0 becomes 1, 1 becomes 0. Right, if you do a not. So if you have 2 bits, 0, 1, and not 0, 1 becomes 1, 0. And if you have 1, 0, 1, 0, right, not this string becomes, all the bits flipped, right? All the bits are flipped. So 1, 0, 1, 0 becomes 0, 1, 0, 1. That's how not operator works, right? And then end means this and this, the 2 bits, only when they're both 1. Okay, you got 1, right? So this is then when we move on to the next concept, which is Boolean operation. In Boolean, we're dealing with 2 values, right? True and false, right? So when you think about AND operator, right, then 2 things have to be true at the same time. Then only then you can say this expression is true, right? So true and true means true. One is true and the other one is false. Then this whole concept, this whole expression is evaluated to false, right? Let's say if 2 is greater than 1 and -1 is greater than 0, let's say one of those is false, right? Then this expression, this whole expression is false, right? Because -1 is not greater than 0, right? That's in Boolean expression. So in this bitwise operator, you got this basic evaluation, right, of the AND operator. And then if you have multiple bits, more than 1 bit, right, it would be each bit, you align those 2 numbers in your calculation. When 2 and 2, when 0 and 0 line up, right, the value is 0. Only when 1 and 1, you have 2 1s, the result is 1. That's how AND operator works, right? This is should be easy to understand. And then or is basically saying that if this is true or that is true, then the result is what, right? So in when you're dealing with all or operator, if either bit is true, the end result is true, is 1, right? So it's 0 or 1 is 1, 1 or 0 is 1, and 1 or 1 is 1, right? And so sometimes this or is written as plus, right? We can see that later on as well. This is kind of like, if you think about it, right? 0 plus 0 is 0. If you're dealing with just one bit, right? 0 plus 1 is 1, right? 1 plus 0 is also 1. And 1 plus 1 in this case is also 1, right? That's how OR works. And then XOR is what they call exclusive OR, right? Exclusive OR means that you can only have one bit is true, right? Then the result is true. Otherwise, if both are false or both are true, if both are true or both are false, then the end result is false, right? Is 0. Shift and shift. L shift is left shift. Left shift means shifting that way, right? Shifting that way. And R shift is shifting this way. So when they write these operators in these problems, they'll write L shift dash n, which is how many bits to shift, right? And when they, I mean, these operators, the shift operators, works this way. So when you do shift left, you fill the right end, right, with zeros, with 0 bits. And if you do right shift, then the left end is filled up with zeros, right? The new bits will be zeros. Then the circular shift is basically like we talked about earlier, right? You move this, but then the bits on the left end for the L circle operator does not disappear, right? It just moves on to the end of the string. Yeah.
Question. So does that mean L shift and R shift they lead to these two bits? After
They just throw them away, right? But any question about these? Okay. But in Python, actually, the L shift and or right shift, yeah. So these shift operators, let me see. Yeah, is somewhat, different, because when you have to understand that these numbers are integers, actually, and usually how the language represents integers is that they use the highest bit as a indicator for the sign of the integer. Okay, in these languages, integers are signed integers. In Python, for example. So when you think about -1, for example, right? This is -0b1. It's binary for -1, right? Actually, this integer would be a I don't know how many bits, right? But in Python, integer is actually an object. So in there, when it's stored in memory, this whole thing is filled up with ones, right? And so if you can, I mean, if you take a look at this, and if you do a right shift, right, it doesn't actually just fill up the right end with 0. All right, it actually fills up the right end with the sign of the integer, which is in this case would be 1 actually, right? So there's a little bit of complication in there, but since we're not dealing with Python here, I was just thinking I will give you some of these language specific features, but you don't have to worry about those in ACSL. Any question about this? Yeah.
What do you mean by integer assigned?
Signed meaning that when you talk about integer, right? Let's say integer value has let's say, let me give you an example in C, right? C has this concept of unsigned integer. Unsigned integer means the integer can only be 0 or above, right? You cannot give it a negative value. Okay, if you do that, it would be either a warning at well, actually the language will not because it's a lower level language. When an integer is a primitive type in C, the primitive type means that it is just really a 32-bit memory. And when you say this integer is unsigned and you give it a -1 value, for example, it'll take it. But when you print it out, and you say, I want to print out this value, right? It'll become a huge number instead of -1. Okay, the reason for that is that when you assign a negative value to an unsigned integer, the language will take it as a, let's say, 32-bit integer in that instance. Okay, the 32-bit integer will have 32 bits of 1 in it, because that's what, when it is signed integer, the highest bit indicates it's signed. Okay, if it's a negative value or positive value. Okay, that's how C deal with signed integers. Okay, so when it's a 32-bit signed integer, the value will be, from -1, right? Or, well, actually minus whatever 31 bits will be the value, right? It's actually, -2 to the 32 to the power of 32 minus 1, right? Oh, yeah, those are language specifics. Okay, but in Python, because an integer is an object, so it actually has a different way of dealing with the sign, right? But when you do this left-right shift, right? When you shift left, it will fill up zeros in the end, right? So for example, this, right? If you do a left shift, it will fill up the right end with zeros. But if you do a right shift, right, it'll fill the left end with 1, actually. These are, when you deal with these, programs, when you write programs, write code in this particular language, you will need to understand and think about these specifics. Yeah. Let me see if I could write here. Okay, I will need to stop sharing, I think. Stop sharing. Okay, then I can write. Am I? Right. Zoom, I have to do this, specific weird co-hosting thing. So this phone is actually the host. Anyway, so if I can write in this, okay. I don't want to do 32 bits because that's a little too long, right? So I'm just say if I have 4-bit integers, 4-bit integers would be, let's say if it's unsigned, right? Let's say uint. This is C language for unsigned integer, right? Let's say if it's 4-bit, then the value would be uint would be from 0, 0, 0, 0 to 1, 1, 1, 1. Right. This is the whole integer value range, right? Let's say if we only have 4 bits, right? And if it's signed integer, it is also 0, 0, 0, 0 to 1, 1, 1, 1, right? Right. But because it's signed, the integer actually has 2 different ranges. 0, right? 0 is in the middle. And then it goes all the way to 0, 1, 1, 1 on the positive side. And it uses the highest bit as the sign of the integer. And then on the negative side, it would be 1, 1, 1, 1. Right? So this in the integer negative integer sense, this actually is this highest bit is the sign of the integer, right? When that bit is 1, means this value is negative, right? And then when the highest bit is 0, it means the integer is positive, right? This is how the language, deal with integers, right? It just, shift the range of the values, right? But if it's unsigned, as you can see, the integer value range will change, right? It goes from 0 to all 1, right? But if you do left shift, right shift, in this case, in the signed integer case, when you shift right, when you do this shift right, this is R shift, right? Or in C language operator, it would be this, right? So if this is actually 1111 in this case, all one bit, an integer with all bits as one, then when you shift right, it'll fill the right-hand side with one, right, with the highest bit. Okay, and in that case, the in this case, when you shift this number with 4 bits, shift it right 4 bits, right? You'll still get 1111, right? The number is still 0. I mean -1 in this case. But if you have this number, a positive number, and you shift it 4 bits right, you'll get all zeros. Right? So that's the difference when you deal with signed integers in these languages, but not in the ACL sense. Okay, in ACSL, if you're dealing with 4 bits, it's just 4 bits. There's no sign or unsigned. There's no concern about that, and then it always fills the if you shift right, it always fills the left-hand side with zeros. You're basically, kind of dealing with like unsigned integer, right? Kind of sense. Again, if you don't, if this is still confusing, just let it go. It doesn't matter that much for the ACSL sense contest. See, how do I get back to? Sharing again. Okay, so let me do sharing again. All right, so
Why are negative zeros and negative products?
In these languages, as I say, right, the way that the languages, tell what the sign of the integer, the way that they tell the sign of the integer is using the highest bit as an indicator of the sign. Does that make sense? Say louder.
Why are the negative zeros and negative products in the language of new Testament?
I couldn't hear the question.
Why are there negative zeros and negative products?
There's no negative zero, but if you talk about signed integer, right? There's minus, there's a negative, there are negative integers, right? It goes from -1 to minus whatever maximum the number of bits can represent.
It's kind of like a zero means positive.
That's only the highest bit.
He's asking why you putting the negatives in front of the bit.
This?
Yeah.
Well, this is basically to tell Python that this is a -1, right? And you don't have to write it this way. I'm just, this Python does take this because this is actually a -1 in binary representation. Right? This is, you can just say -1. It means the same thing, right? The 1 is just 1, and it's the same value in binary or in decimal, right? It's still 1. But when you give it a sign, then if it is again like I don't know if you can read this. It's a little too small. So if it is a -1, right? If it's a signed integer, -1 would be if it's 4-bit integer, right? It would be 1111 as the language stores it in memory. That's just how these numbers are, dealt with in languages. Because you have to have a way to say to tell if an integer is negative or positive, right? Right. And the easiest way for that indication to indicate if a number is negative or positive is to use 1 bit as an indicator, right? So the convention for all these, for languages like C is to use the highest bit as the indicator, right? There's no, I guess, particularly why do you use the highest bit, not the least bit? It's because it's much easier when you compute, when you actually do like addition or subtraction and all, I mean those kind of operations in machine language, when you use the highest bit. Any more questions or?
I'm just wondering, did they sign an unsigned integer? If you send a 1111, how the computer know the one to sign integer or unsigned?
Computers don't really know, right? But when you do addition, for example, with 2 numbers, it's easy to do it, to use the highest bit as when you use the highest bit as the indicator, as the sign, it is actually much easier to design the circuit to perform addition and subtraction that way, right? Computers doesn't really know if a number is signed or unsigned, but if you do have the highest bit as the sign, and when you do addition, for example, if you do 0 plus -1, right? So you get 0 is in here, 0 is all 0, right? 4 zeros in a 4-bit integer, and -1 is 1111. If you think about it, if you do 0000 plus 1111, it's very easy to design the circuit to make it just, the result will just be 1111, right? It turns out that that is -1, right? Again, I'm not going into all those details of like how do you actually do addition, for example, with digital circuits, right? Because we understand what addition means. Computers don't really. What computers do is actually these bitwise operations, right? And or XOR and XNOR, and just all these kind of bitwise, stuff. Right? That's all computers do actually. And it turns out that when you design your circuit using a series of XOR gates, for example, and you put all those bits through, and on the output side, you will get the result of addition, right? That, if you really want to prove that, you can do that, but in this class, we'll just say that's the case. right? So you can have a series of these simple gates, bitwise operators, right? And then you run these numbers through that, right, in binary, through those gates. And on the output side, you'll get the result of addition. Addition is actually, or as sometimes it's called, it's actually a series of XOR gates, right? And that is actually the very basic of computer integer instructions, right? That's how they work. And then initially in the very first generation of computer chip design, it only had addition. That's all the initial first generation, let's say, integrated circuits can do. And then when you want to do subtraction, you basically turn the numbers. You have to convert the numbers initially and then run it through addition to get the result of subtraction, right? And then like multiplication and all that is also done that way. Because multiplication, if you think of binary multiplication, it's actually the number, right? And then you shift the number by certain bits, right? And then do addition, and then shift it again, do addition, and shift it again, do addition, right? That's how multiplication is actually done in the very first generation of computers, microchips, if you want, right? Obviously, today's microchips, the CPUs are much more powerful than that, but that's how how these things were done initially. I think we're spending a lot of time in this. Yeah.
So are the negative signs just not necessary? Just like not necessary? Or are they just like
In ACSL, like I said, in ACSL, they don't have that concept. Okay. In ACSL, you're actually just dealing with bits. So there's nothing about sign or anything. And or you can just consider this all unsigned, right? Meaning that you always have, just think about it, you always have zeros on the end, right? When you do shifts. So however you shift, you always fill the end with 0. That's how ACSL does it. Okay. I'm talking about all those is just telling you that if you really are writing code with in Python or in other languages, you have to, think differently.
Actually, just one last question.
Okay.
So why is like the one left shift to like 4 is like 1 6? I felt like the bit just like one.
That you can basically think about it this way, right? One, let's say if you have, let's say 8 bits, right? 8 bits, 1 would be 0 0 0 0 1 1 0 0 0 1, right? That's 1, right? In here, it's very small. Let me see if I can. Oh, hold on. Stop sharing. That's 1, right? And if you shift it left 4 bits, what do you get? You're basically moving this 1 over here, right? So this becomes 0 0 0 1, and you fill the right-hand side with zeros, right? That's the result, right?
So what you fill in with is what matches with the first one, the first job down the very up.
Sorry, what? When you do left shift, you're moving all these bits leftward, right? So basically, you're moving this 0 over here, this 0 over here, this one over here, and this one over here. So this is the result of this 4-bit left shift. Does that make sense? Or
So when you move it, so you shift it, is what you fill the space with is like what matches with the first bit you see, like
these four bits would be these 4 bits.
yeah, I know, but like the ones behind
These?
yeah, so do you always fill them with 0, or do you just fill them with whatever's in the first bit of the
No, you always fill them with 0. That's how shift works. Right.
I got kind of confused with the vowels.
And even if you're dealing with the circular shift, right, the result is also this, right? Because when you move these 4 bits to the end here, you're also getting the same result in this case, right? But if you are dealing with -1, right? -1 would be 1 1 1 1 1 1 1 1, right? Right. And then if you're dealing with the ACSL right shift 4, right, then the result would be 1 1 1 1. These 4 bits would be gone, right, moved off of the range, and you got these 4 bits filled up with zeros in the ACSL operation, right? And so this will give you 15, right? If you do it in Python, right? Or I mean, if you print it out as a decimal integer, this would give you 15. And that's just how shift works. Now, how do I go back to? Okay, so okay. So in the ACSL, actually in other languages too, I think. This is the precedence or order of precedence when you do these kind of operations, right? So the unary operators go first. Actually, we're missing the parentheses, right? You can also have parentheses in these expressions. So parentheses always go first. And then the unary means not shift, means that it only has one operand, right? Those go first, and then and or and or these kind of operators. So if you think about it, it's kind of makes kind of sense if you think about it as like and is sort of like multiplication, right? Or x or these are sort of like addition and subtraction, right? Type of operator. So the order of precedence, I mean, you can kind of remember it that way. Next is Boolean algebra. Again, you can see that the operators are this set, right? Not and or x nor, right? And you can actually, XOR could be turned into this, right? And actually, sorry about that. This needs to have parentheses. Oops, sorry. Right. So again, this is how they're written, right? Not and or. Again, these kind of look like multiplication, right? And it looks like multiplication, or looks like addition, and XOR, XNOR, and that's their equivalent, equivalent expression, right? And so, and again, if well, not is basically the opposite of whatever the input is, right? Not true becomes false, right? The same thing. Not false equals to true, right? And means if both are true, then it's true, right? So if, or a lot of times in languages, we use a non-zero value to represent true, or we can say we use 1 to represent true, right? If we're dealing with binary values, and 0 means false, or is the other way, right? True is either 1 or both are true. XOR means is exclusive or. So if it's true, means that then that either one but not both are true, right? And XNOR is the opposite of XOR, or the not of XOR. So yeah, a lot of times you can consider Boolean values as single bit binary, right? You're just dealing with a single bit, and then there's no, you can't do carry over to the second bit. There's no 2 bits, right? There's no more than 1 bit. That's how Boolean stuff works, right? Do you guys want to take 5 minutes? Okay, let's take 5 minutes.
Why are we doing everything big idea?
Give me 1 second. All right. Okay, these are Boolean operators, right? Again, we're talking about the same set of, pretty much the same set of lines, really, right? So there are these laws about Boolean algebra. Okay, and these actually, if you think about elementary school math, a lot of these things apply. You think about addition, right? You always have the same rules, the same law that work over there, right? Commutative means, right, if you have X and Y. And if you switch the two operands, Y and X, the result is the same, right? And so for OR, for XOR, for XNOR, they all have this characteristic. And if you think about multiplication and addition, they also have this feature, right? Like A times B equals B times A, right? A plus B equals B plus A, right? You have this same kind of law in those primitive math level, right? And associative means that if you have X and Y and Z, you have the parentheses to indicate that which part go first, right? It would be equal to X and Y and Z, right? So, and idempotent law means, right, if you have X or X, it would be equal to X, right? X and X would also means X, right? These are the very simple laws, actually. It's not very difficult to understand, but you do need to, remember these laws, so that when you try to find solutions, when you work on those ACSL problems, right, these laws help. You guys? Lock? Oh. All right. Thank you, guys. So so these laws are very simple stuff, right? And a lot of times you can just think about, these will simplify things, right? These simplify things. So if you have 2x, right, it becomes 1. And if you have x plus 1, x or 1, right, this always equals true, right? In Boolean sense, if you say if something or true, right? Or if you say if true, then it's always true, right? If you say if true or something else, then the value of that expression is always true, right? So this is basically how, you can think of these rules in those Boolean terms, right? Let's say this, right? It basically means if something, either true or false, and false, then this whole expression is false, right? Because false is just false. You end whatever, it's still false, right? If you say false and true, the result is always false, right? So if you have a false in there, the result is always false. And then identity law is, sort of, but these two laws kind of complement each other, sort of, right? And complement law, actually, again, is also a way to simplify things. Let's say if x or not x, that's always true, right? So whatever x is, it would be if true or false, it's false, it's true, right? Or if x is false, then if true or not true, right? Or if false or not false, it's always true. And so with all these rules, these are basically ways to give us, these are we use these laws to simplify Boolean expressions, as we can see later on. You guys, if you want to take some notes, it's good. You can actually, when you get home, all these are on the wiki site, okay, ACSL wiki, and also I'll make this available for you later on. Any question about these? Oh, okay, so now let's work on some of these contest problems from ACSL. And because I used the Google online presentation editor to work on these things, and there's no way to write these expressions elegantly, so I used a document. Oh, sorry. Okay, let's quit this mode. Okay, so these are the problems that that are taken out of the ACSL wiki site, and also other learning material. So let's say this expression is a Boolean expression, right? It means A and A or B, and then this whole part negated, right? Or B and not A, and then this whole thing negated again, right? So how do we simplify this? We use those laws. And this is the De Morgan's law, and this is the particular one that I'm using here, right? So this help us break up the first or the top level not operator, right? Because this whole thing is basically this part, right? This part or this part, and then negated, right? So if we treat this A plus A and A plus B negated, right, as one item, and then B negative A as one item, right? And then this or becomes one operator, right? And so we can take out the first level not, and that expression is equivalent to this. Any question? Right, this is basically if X is this whole thing, right? This first part, we take that as X and this as Y, right? It's basically X or Y and then negated. That would be not X and not Y, right? That's a law, right? That's a simple law. And we apply this to that expression so that we can take out this first level of not, right? And then this becomes two parts, right? Become these two parts. And then we use the double negation law, right? If we double not X equals X, right? Because not X is basically flipping it over, right? And then if you do negation again, not X, the result is X, right? It's not, that should be easy to understand, right? And so we can take the double negation off of this part. Right? And so that part becomes this, right? A and A or B. Right? This is the only change that I made here using the double negation law. Right? And now again, in this, I can use this item out in the De Morgan's law, right? X and Y negation equals not X or not Y, right? These are simple laws, and if you guys, you need to basically, not just understand these, but really get them into your head so that you can apply them easily, right? When you see these things, you immediately know what to do with this, right? So that becomes not B plus not A, right? This part changes into this, right? And then with this part, we apply the absorption law. And that is, absorption law is if X and X or Y, right? And the result is, drop this part, and the result is X, right? And so this part becomes A, right? And now actually, then we can use this double negation law on this part, right? On this A. So A, not A, right? This is not A, becomes A, right? And this, again, we use the absorption law on this whole thing, right? Because this you can use, actually I should kind of, I jumped over one step here, right? So this equals to A plus A or not B, right? This is not B or A. You can commutate those two operands, right? What are you guys talking about?
Remove my pencil. Oh, me too.
We don't have much time, so just hold on for a little bit, okay? So basically, this complex expression is simplified to A, right? Another way to do this type of solution sometimes is to use this so-called truth table. Right? Truth table means that, for example, with this expression, it's similar to what we did above, right? But the way to get the solution of this, the solution is find all the ordered pairs, right? A and B. Find all the bits, the pairs of these bits, or these values, Boolean values, that make this thing true, right? Actually, if you do the simplification, you can also get that simplified to just A, right? But if you just use the truth table, then this is how it works, right? These two columns are A and B, right? These are all the combinations of what A and B could possibly be, right? So there are 4 combinations, right? 0, 0, 0, 1, 1, 0, 1, 1. Right? There's two Boolean values. You can all, that's all the combinations you can have. And then, right, with each part in this expression, we use a column to represent the value. Right, so A or B is in here, right, in this expression, right? And A and not B is also in this expression. What else? Wait, did I get? Oh, so I got this wrong, actually. This is actually not A, B, not A, not. So to correct this expression, because actually in the table I got them right? So it's not A. Well, I'll correct them later. So the expression is actually this, right, in column 8. So that not A is in the expression. You just 5 more minutes. You hold for 5 minutes. Okay. So this is how this truth table works, right? You basically use a column to represent one operation in this expression, right? So A plus A or B is in there. Not A is in there, and then not A and B is in there, right? So we break them apart in this way, right? So so you got A or B is in there, so we do this operation, A or B, and this is their other values, right? And then not A or B is this part, right? Is this part of the expression. We use one column for that. And then not A, sorry, here is one column. And then we do not A and B is another column, right? And then we get to this, right? Combine those parts, we get to this column, and then we get to this column. So for the whole expression to be true, these are the 2 rows that are true, right? And so when come over to this side, these are the pairs that we get, right? So the result is 1 0, right? 1 0 1 1, right? If you think about it, if you simplify this whole expression down to A, it means as long as A is true, the whole expression is true, right? So B really doesn't matter in this case, right? So B could be either 1 or 0. The whole expression is true, right? And so that's the 2 pairs that makes the whole expression true. And the next problem, again, is another simplification rule. So if you look at this whole, complex expression, and the way to simplify them, again, is using these laws to break the overarching knot first. Right, that's basically a trick for starting with these kind of simplification problems, right? And so if you have this whole thing as one item, you need to break it apart. So to do that, you always use the De Morgan's law, right? Either one. So here you have not A or B, and then an overarching knot over there, right? So that becomes this, right? Not A and not B. And this part too, right? So I'm just combining those 2 operations into this one step, but using the same law, right? So that also becomes this part, right? And then using the double negation rule, you can, take out the double negations. One is here and another one is here, right? So that becomes this. Right? And now, because this is actually end, right? So we can move this around. That's called the commutative law, right? Because all these items in between them are end, right? End operators. So we can move this part, right? The whole thing in this parenthesis over here, right? The reason that I'm moving them is eventually get to A and not A, right? A and not A, put these two together, then it's the complement law, right? If you have X and not X, that's always false, right? Something and not something could not be both true at the same time. So it's always false. That gives you a always false part in this whole expression, right? So you got a 0 and whatever, I don't care now, right? Whatever the rest could be, doesn't matter. So you're using this annihilator law, basically that says if you have a false item in there and something else, that something else doesn't matter anymore, right? So the result of this expression is always 0, always false, right? So basically this is this is how you simplify these things. So you basically have to break apart this kind of components first, right? So if you break that apart and then you use other laws to either combine them, right, annihilate them, so some components can be ignored, can be dropped, right, and then that simplify the whole thing. These are simple problems and we run out of time, so I was going to next time when we come back, we'll have some of these problems to work with. Right, just prepare for that. So we'll have a quiz probably next time. It will be these type of problems.
It's not that hard. It's not that hard. I was looking at it. It's not that hard.